So determine whether the table represents linear or non-linear function. Now we know that it is a function because first off, none of the x values repeat, so it couldn't possibly be a non-function. It has to be a function. But in order to figure out if this one is linear or not, we got to find the rate of change between each of the ordered pairs until we see that there's a difference. So remember, we are looking for a slope here, so it's rise over run, and rise is y's. So from here, my rise, it goes from 1 to 16, that's up 15 right there. So that's my numerator, up 15 is positive 15. And then the run is from 1 to 4, that's to the right 3. So to the right 3, 15 divided by 3 is 5. And that would be the slope between these 2 points. Now if this is linear, it has to be the same slope through all of the points, in between all the points. So I'm going to go from 16 to 49. And to get that, how far up that goes, I just do 49 minus 16, which is 33. Okay, so this new slope has a numerator of 33. But I have to compare it with the run as well. So from 4 to 7, that's to the right 3 again. So 33 divided by 3, that gives me 11. These two are not the same. 5 and 11 are not the same. So I don't even need to check on this last ordered pair. I know right now that this is not linear. Okay, which means if you were to put this on a graph, just between these 3 points, you'd see some curvature of some sort. So here's our objective for the day. I can sketch and interpret graphs from any situation. And the second objective, I can determine when graphs are manipulative. Take a minute and copy these down, please. If you're still copying these down, finish. But there's a lot of math in this class that I think a lot of you have realized is pretty worthless. You can go home and say to your parents or guardians, hey, when was the last time you used this stuff? And they'll probably say never. Or maybe when they were in 8th grade, like you are. This is not one of those lessons. Okay, now I'm not saying that your parents know how to do this stuff, because there's a lot of older people who don't know how to interpret graphs. So why is this important? It's because, and I'm saying this very directly so that you understand, if you can make graphs, most people don't understand graphs. Okay, that means you can, if you wanted to, control them if you would like. What this also means is that if you can't learn how to interpret graphs, then you'll never know if people are trying to control you with them. Because here's the problem, right? Especially during the political season, you see a lot of graphs out there, and like, hey, look at my graph, and this is what it says, and this is what you should believe about my graph. Well, if you just take them at their word for it, if you can't understand what the graph is saying, then you may believe those people. And then you may, I don't know, vote a certain way because you think, this person was either telling the truth or I trust this person, which is one of the worst things you can do. You should only trust yourself, at least to start with, and you should look at the information and make sure that it is valid, okay? But graphs, most people are like, I don't understand graphs, so I believe this person because they know how to do graphs. And that's a bad way to go about life, okay? So this is one of those lessons that actually can help you, not only in the future, but now as well. So here is a graph. We got distance and Tim. I'm going to change that to time, though. That's better. Okay, so we got labels for the y-axis. Remember, the y's are the dependent variable, and the x's are the independent variable, that's time. But you'll notice, just without reading any of the words, that there's no scale on either the x or the y-axis. That's on purpose. This is what is called a qualitative graph. But just that much right there, that there is no scale on this, that should worry you. You should wonder, why is there no scale? And is it going to be numeric? If it's not numeric, then why is it not numeric? And you can see, and as we go through this problem, I just want you to think, not necessarily how it's done, but how you could, if you wanted to, manipulate other people into thinking certain things about your graph. And again, I'm not encouraging you to manipulate people, but you at least have to see when people try to manipulate you, because they will. Zach walks home from school each day. Sketch a graph of Zach's distance from school as a function of time since the bell rang if the following happens. When the bell rings, Zach runs to his locker to grab his books and starts walking home. When he's about halfway home, he realizes that he forgot his math book, so he turns around and runs back to school. After retrieving his math book, he realizes that he is going to be late, so he sprints home. Now, it may take several readings of these types of problems before you understand how you should make your graph. But again, if you think, how could I actually manipulate this to make people think a certain thing? That's going to be the better option for you, okay? So the first thing it says is that we know that Zach is walking from school to home. Right? It's a distance, school's a function. Zach walks home from school. There we go. Okay, so we know he's going, the distance is from school to home. Now he's going to start at school, so I'm going to put school right here. This would be 0. I'm going to label it a little different, school, okay? So this is where he starts. We know he should end at home, right? So up here at the top, I don't know how far it is to home, but I know that's the farthest distance that he should reach is home. If he goes past home, then he's not home, okay? Now another part that's important for us is that it said that about halfway home, right here, he realized something. So we need to acknowledge that for distance as well. So right here, I'm going to say that's right in between, but that's halfway home. Okay. All right, so we got our distances down pretty good. But now what happened? Let's look at our timeline right here. So it says, this is what happens. When the bell rings, Zach runs to his locker to grab his books and starts walking home. So I'm going to start with just that the bell's going to ring. He's going to get his locker. He's going to go to his locker and grab his books. Okay, so I'm going to start right there. I'm going to say right here, this will be 0 for me, but that's when the bell rings. Okay, well, what does he do when the bell rings? He's going to go to his locker. So I'll say, some kind of timeline like this right here. That's when he's at his locker. And he's grabbing his books, right? So I can connect those 2 points because he's still at school. That's what this line is right there. He's at school. He's just running to his locker, grabbing his books. Okay, now, right here, there's a difference between what's going to happen, which we will see. Right, so we already acknowledge the bell rings, and then Zach runs to his locker. Now he's going to grab his books, but then what happens? He's going to start walking home. Now the reason why this is important is because later on, he's going to realize that he forgot a math book, and he's going to run back to school, and then finally he'll grab that book, and then he will sprint home. So there's a difference in these words: walking, running, and sprinting. So I need to acknowledge that on my graph with different types of lines, and here's what I mean by that. So walking would be at a slower pace. Okay, that means that in relationship to distance and time, it's going to be a more flatter line, flatter line. There we go. A more flat line. Running is faster than walking, so if I make my walking kind of shallow, then I've got to make my running steeper. But sprinting is even faster than running, and so I've got to make that line even steeper in one of the directions. Okay. So right here it says he's gonna start walking home. Right. Now we know that he'll get halfway home. So he's walking and he gets halfway home. So I'm gonna put it over here. Right, and we'll say he's walking at a constant rate. Hopefully your lines are straighter than mine, but that's good enough for me. All right, so that gets him halfway home. But then, so yeah, we'll say that we'll list this. Walks home. But then what happens? He's got to go back, right? This is where he's going to run back. And I'll do this one in green. So I got to make my green line steeper than the purple one. So I guess the purple one would be about right here. So I'm going to make it a little bit steeper, putting it a little bit closer. I don't know, about right there, okay? So we can see that green line. It looks like it might be as steep, but it's a little bit steeper. It's just in the downwards direction because what's he doing? He's going back to school to grab his book. Okay, so he's going to run back. All right. Now, of course, he'll have to spend some time at the school in order to grab his book. So I'm going to make that, we'll make that this line right here, a little bit, just for a little bit, okay? So this is where he's going to grab his book. Now, since he's going to be sprinting home, this means that from school, he's got to get home, but he's got to get home at a steeper line than even the running line right here. So sprinting home, of course, that will be in orange. And I'll just try to reach the end here on my time line. So this would be the end when he gets home. So you can follow that up right here. In the end, where should he be at the end? He should be home. We'll see how this kind of connects with this home distance right here. So we need to get from where he is at the end of school, right here, this book, and he's got to sprint home. See how that does actually create a steeper line for us. If this will work. I don't know, something like this. And that orange line now is steeper than both the green or the purple one. But this is now him sprinting home. Now the way that I have this, everything's pretty linear, right? We got straight lines to straight lines. Now I'm not saying that the whole thing is linear, but each section itself is linear. So some of you may have made these slightly curvy. Remember, this one's only kind of wavy because my hand isn't stable enough, but you could have made some curvature on these if you'd like, all right? But this is approximately what your graph should look like. And that acknowledges everything that happened in the story. I think we got everything. Bell rings, walks home. Again, that's halfway home right there. He's going to run back. He grab his book, so he's at the school right there. So again, that's 0 at school. He's going to sprint home. Boom, we did it. All right, now you see, just from this, just the way that I've interpreted it, there we go. Some of you may have made different lines on this, and maybe even for good reason. But you see how easy it is to make interpretations different, right? And so, like, if I really wanted to make old Zach look really slow, I would just make this line even less steep than it is. You see what I'm saying? I'd put it way over here. Or maybe if I want to make him look like he can sprint super fast, then I would make this line even steeper right there, okay? So it's very easy to manipulate graphs in order to control people's thoughts. But right now, all I really want you guys to do is, I never want you guys to do it, but people will try to do it to you. You have to be able to see when people are trying to manipulate you, okay? One of the main things you need to do with these problems is to read them. Actually make the mistake of not reading these, which is not good, okay? But you should. So let's go and read it. A concert for a popular rock group is sold out. The arena holds 8,000 people. The rock group is scheduled to take the stage at 8 p.m. A band that is not very well known is opening for the rock band at 6:30 p.m. The rock band is scheduled to play for 2 hours, and the staff working the concert have been told that the arena must be cleared of people by 11:30 p.m. Sketch a graph of the number of people in the arena from 5 p.m. to midnight. Here the time 0 on the grid below, I guess above in this case, is 5 p.m. Okay. Now just this bottom part, this last thing that we read right there, time 0 on the grid below is 5 p.m. Now I assume that if you ever saw 0 for time, you'd be thinking hours, not necessarily 5 p.m. So you can see right there already that this graph is kind of manipulative, okay? So I'm gonna go in and I'm gonna label this 0, that would be 5 p.m. Okay, so that means that 1, in this case, that should be, well, 6 p.m. 2, 7 p.m. 3 would be 8 p.m., 4, 9 p.m., and the last few here, so 5 is 10 p.m., 6 is 11 p.m., 7 is 12 a.m., and 8 there is 1 a.m., okay? So this is a little bit more accurate for me. That way I don't have to think about, well, what is between 1 and 2, or what is 1 and 2, or 7 or 8. I have it labeled already. And you notice right here that they've already given us not only the label for the y-axis, so we know it's the dependent variable, but they scaled it for us as well, which actually, yeah, that can worry you sometimes. Now I'm going to show you guys this. I just really hope that someday you don't grow up, become a mathematician person, like a really big-time math nerd, and then use this for evil purposes, because people do. The scale on this one is good, but it was given to us. We didn't make this scale. You see how it's going up by 1,000 every time? That's a good thing. It's just that it was given to us, which was kind of not a good thing. But sometimes you'll see a scale that doesn't go up by the same amount, like this one will be 10, and then 20, then suddenly 3,000. What the crap is that, right? So, if you ever see stuff like that, just know that people are trying to control you with the way that their graphs look, which is, it's a pretty big scumbag move. All right, now that we have that set up, we know that the y-axis is number of people, and the x-axis is time, which in this case is actual time. You could say in hours, that's fine. But notice that the arena holds 8,000 people, okay? So that's the maximum capacity of the building. But the rock group is scheduled to take the stage at 8 p.m. So we've already got 8 p.m. right there labeled. And so I'm going to go in here and say this is when the actual rock band, that's when they're going to take the stage, okay? Now, it said that it's a sold-out arena, which means that at 8 p.m., right? That's when they take the stage. At 8 p.m., that we would expect the sold-out arena to have full capacity, which we know is 8,000 people. So for this 8 p.m. right here, I'm just going to put a line up here. Hopefully your lines are straighter than mine. But I know that we should reach this point at 8 p.m. Now, I'm not familiar with concerts like this to know if this is actually true. Maybe not everyone's there by now. I don't know. But that's the thing with these graphs, these types of graphs are called qualitative graphs, is that they're kind of subjective to who's interpreting the information. So what that means as well is that your graph may not actually look exactly like mine, but it should look pretty similar to mine, okay? All right, so there's our first piece of information. We got it on the graph. There's that point. Let's look at the rest of the information. A band that is not very well known is opening for the rock band at 6:30 p.m. So this lesser known rock band, they're going to come on stage at 6:30. So where's 6:30? It's right between 1 and 2. That's between 6 and 7 p.m. That'd be 6:30, okay? 6:30 p.m. Now that's when the rock group, the opening band, I guess, that's when they take the stage. Now they're lesser known. What does that mean? I don't know. Does that mean that they're lesser known, like maybe only 1,000 people, maybe 50 people show up? I have no idea what that means. Now, the one thing I would say that we would probably not expect at this point, is probably not 8,000 people. I could be wrong on that, okay? But I'm going to go with just right in the middle, between 8,000 and 0. I'm going to put in 4,000, okay? And again, since you're interpreting this on your own, you get to choose where that is. Okay, so again, I'm just following the timeline up to this point at 4,000, right? Just like we did with the red dot, it follows over here to 8,000, okay? So these are some points that we have, and we'll worry about connecting them later, but let's read the rest of this. And notice that we've already read it once. This is the second time going through it, maybe the third, but you may have to read these and reread these several times. The rock band is scheduled to play for 2 hours, and the staff working the concert have been told that the arena must be clear to people by 11:30 p.m. So this rock band, they're going to go, that's how long they're scheduled, 2 hours. So if they're starting at 8 up here, then they're going to go for 2 hours. That would be 10 p.m., right? That's when they're going to end the show. That would be this point, which means that pretty much throughout the length that they're playing, we're going to say that the arena is at full capacity. Now, some of you may say, well, yeah, but at these rock concerts, sometimes they fill them past capacity, so we have to line up here. All right, that's fine. I'm not doing that because I'm interpreting the graph, but yours may look different, okay? Now, the other thing it said on this line, it said that the staff, they got to have it clear to people by 11:30. Now, I don't know rock concerts very well, but I know back in like the 70s and 80s, they were freaking nuts, dude. So, at 11:30, it's like, hey, everyone's got to clear out. You think those groupies are clearing out, dude? No, they're not clearing out. And again, this is just my interpretation, but that's 11:30 p.m., right? I'm going to say there's still some people running around. Maybe there's, a mall somewhere, people punching each other, and I don't know how those rock concerts work, okay? But I'm going to put this point right here, and that's when they're supposed to be empty. It's supposed to be empty. But I'll give this, and by the way, if some of you put the point right here, right on that axis, go ahead. Because you may think, well, literally, hey, this is it's supposed to be cleared at 11:30. Okay, I'm a math person. I'm not supposed to be creative, but I just was. Sorry about that. So now that we have this, what do we got? Do we got the sketch a graph from 5 to midnight? Okay, I'm going to go all the way to 1 a.m. by the way. So let's put this line on the graph, and let's see if we can help you guys be a little creative on your interpretations. Not that you should. Now think about it like this, okay? Let's say that I want to trick people into thinking, man, this is a rockin' thing, right? Then I'd say I would want the graph to look something like this. Why like this? Because it shows that the number of people coming into the arena was increasing very, very, very fast, quickly, and then it kind of levels off to this point that I had already put on the graph. Now, especially if I was looking at the opening band, like, man, I hate those guys. I hate them so much. Then I would say, look at this. I'm just going to put the line like this one. Or even I wouldn't even put the point here. Like I said, remember, you could have just put the point down here. Like this band, this opening band, they suck. And I hate their guts, so I'm going to show that the graph would look like this. Okay, now they're not even half as popular as I have them right now. See what I'm saying? Okay. Now, if you want to be all mathematical about this, because right now we haven't seen any curving lines like that necessarily, just put a straight line like this. Okay. Now, even with that, some of you guys are like, well, couldn't I just put a line like this one? Like, at 5 p.m., there was already 4,000 people in the arena. Sure, I don't know. They didn't say anything about opening the arena or when they open. Is 8,000 people a lot for an arena? I have no idea. Is people camping outside waiting to get in? No idea, dude. But if you want to think that, go ahead. Now remember, one of our objectives is telling if a graph is manipulative. You see what I'm saying? How easy this can be manipulated, right? And it's kind of the same thing for this next group. By the way, I'm gonna take that line off. I'm gonna make it straight because I'm a math nerd. Okay. And then you can pretty much do the same thing with connecting these next couple points. I guess for me though, I would anticipate that there's going to be people. It would probably be full capacity before the rock band takes stage because they're super popular. You know what I'm saying? And then I would connect these two lines, right? Now I made those straight lines. Is that really going to happen? Probably not, but it's a math class, okay? And so how about when the rock band they finish right here at the end of the green line, whatever, maybe they're staying around and then the security people get their tasers out and start really getting people out. But then there's always the stragglers, right? So maybe it's not fully empty, but Then later on, it gets empty. They get their job done, and by 1 a.m., it's empty. They're preparing for whatever's on the next day. And yeah, I know I made this line curvy. There you go. So on this one though, we got a science teacher. He's got this beaker right here. You're gonna fill him with water from a faucet at a constant rate. Well, that's very nice of him. Gonna fill this at a constant rate. The job is to sketch the graph and the height of water in each of the beakers over time. Let's just start with this one. Now you'll notice that the top of the beaker, right here, at the top of the beaker, the water level can't go past the top of the beaker, right? I know it's off the y-axis right there. I'm not too worried about that. Now, the nice thing is the bottom of the beaker is when the beaker is empty, but that does line up with the graph, so that's an empty beaker. Okay, so what are we comparing right here? Well, we're comparing the height of the water over time. So height, in this case, is our y-axis, and time here is going to be our x-axis. Now we don't know, you could say time in seconds, I really don't care. I just know that this teacher's gonna fill this beaker up all the way to the top, and we have to graph it, okay? So just think about it like this. Well, it's not really a good animation, but it'll do. Okay, so the teacher starts pouring water into this sucker, and it starts going up. Up, 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 like this, okay? Now, if I had done this maybe with more technology, that'd look better. And you can see the moment that the water gets to the very top here, it's just gonna start pouring out, so you cannot get above the top of the beaker. But just going back on that, okay? How did that work when we did this? Well, it fills at a constant rate, which means that we're looking at a line that it'd be a straight line, starting with what I would say from the empty beaker, and even for my time right here, I'm going to say right here at the very end, even for the time, that's a full beaker, okay? Why is that important? It's because when the time gets to the full beaker, that should be in height the top of the beaker. See what I'm saying? So I need to reach this point from the empty beaker for both the x and y axis. Well, that's not too bad. Again, like I said, that should be a straight line like this. Okay? So that's what the graph would look like on this one. Well, how do you get this? Maybe can this line be curved in a certain way? Sure it can. If you start curving the edges or making them wider or thinner, something like that. All right? How about this beaker? So once again, we have some levels that we need to acknowledge, right? We got the empty beaker right here. At the very bottom, there's our empty beaker. And again, I'm going to make the height the y-axis here. Which means that the top of the beaker, that'd be a full beaker right there, okay? This one right here, that's the top of beaker. So when I compare this with time, which is my x-axis, the very end of my time line here, that should be a full beaker. Now I know a full beaker isn't in like a unit in time, but we know in time that the very end of the timeline needs to be the full beaker. So up here at the top, let's go and write this up here. Again, the two lines need to match up here at the top. Okay, so when we get to the top of the beaker, it needs to be right here. Well, fair enough. Let's look at the beaker then. Okay, so there's a few different parts of the beaker that we have to acknowledge. Okay, for example, this beaker kind of curves outwards from the middle, but then as soon as it hits this point right here, then it starts to curve back inwards, and that means that for this graph, I'm going to put this down. We'll pretend like my line is straight, but right there, that's where we should reach a point where the line is pretty much going to change. Okay, and then, just from right there, then it's going to kind of curve backwards in like this until it gets to this point. So we'll just acknowledge right here. Again, we'll pretend like my lines are straight. Right there, that's when we get to this kind of straight neck on the beaker, which is this line right here, right? And we've already acknowledged between where this changes from curvature to a straight line to the top of the beaker right there, okay? Well, what's happening in this beaker? Well, if you start to fill this with water, right here at the very bottom, you see it's thin, so it starts filling up, but as it fills up, it's getting wider, which means that it would start filling up slower, because it's got to get wider and wider. See that? So in our graph, to make this look like it's getting slower and slower, slow indicates that the line would be more shallow on this one. So that means that this line, it would start getting more and more shallow as you go. So that would look something like this, okay? Because it starts faster because it's thin in the bottom, and then it gets slower as you move up. Now that we're at this point though in height, now as we fill up this beaker, it's wide, but now it gets thinner and thinner as we get towards this bottleneck right there. Okay, so that means as it gets thinner and thinner, it needs to fill up faster, and so this line needs to get steeper and steeper as we move in time. So that would look, I'm going to emphasize this, but it would look, I don't know, something like this. Okay, it gets steeper and steeper as you move to the right, and then once we hit this bottleneck right here, then it moves at a constant rate just like we saw on the last problem, okay? So that's okay. All right, so that's the graph, and again, I did emphasize these so that we can see the differences between them. And unfortunately, I say that, like, I emphasize this just so that we can understand it better. Just so you understand, that is a manipulative form of using graphs. Hey, I emphasized that this one is curving upwards, so that you can see that it curves upwards. People say that to you using graphs, and if you don't know what the crap you're looking at, they now have control over you because you didn't ask any questions. Yeah, but what does the original graph look like? Well, we don't care because we're just trying to emphasize what's happening. Okay, well, I would like to see the original, okay? Because really, once we get to this point, the rate of change should be constant, which means that once you get to a slope right here, it should just move in with this green line, okay? So when people start saying things like that, you gotta start worrying. And once again, your graph maybe look a little different, but it shouldn't look very much different. It just should look a little different. Are those little differences big sometimes? Yeah, they are, depending on the scale that's being used and how much you actually want to control the people looking at your graph. All right, for this one, we got a graph. It says Ben is taking his family on a road trip to visit their cousins. The graph shows their journey. On the graph, label any increasing or decreasing. And just so we can remember this stuff, increasing and decreasing, this is talking about slope. Okay, so that means if it's increasing, it should be going up. And if it's decreasing, it should be going down. But specifically, it would be going up or down from left to right. Okay, now before we start labeling these, which really isn't too bad, what you see is that this line is going downwards. Well, what's the labels we're looking at? We got distance from Las Vegas in miles, and we have time in hours, right? So this means that once they get here to 0, that's when they are actually at Las Vegas. I guess Ben and his family. But right here, this 0450, that's how far they are when they start keeping track. Is that how far away they live? They didn't tell us. So we can't say for sure. It's just that they're starting 450 miles away, whatever that means. Now the straight line here indicates that they're traveling at a constant rate, which we know doesn't really happen, not on the freeway, not even with cruise control. And this line is pretty steep. In fact, it's steeper than this one, which means they're traveling faster right here through this line than they are right here. Why does this one get more flat then? Why are they going slower? Well, they're getting closer to Las Vegas, right? And again, I don't know, 3 hours seems like plenty. But the moment that they get into Las Vegas right here, then the speed increases again. So what does this mean then for these flat lines? The flat lines indicate that the distance is not changing. They're not getting closer or further away from Las Vegas on these two flat lines. Now, we don't know what's happening. Maybe they're taking a nap. Maybe they're getting something to eat. That just means they're not moving. That's all. So let's identify these values. We got up and down. And I see just to start out with, they're going down, right? The value, the distance is getting lower, which means that this one's decreasing. I'll put D for decreasing, okay? And I'll use I for increasing. Now right here we see that it gets flat, but again, that flat line right there in green means they're just not moving. They've stopped. But then, this line right here, it's going down from left to right, which means this one is decreasing. Then there's a shift, right? They get to Las Vegas and then they're just moving away. It is at a faster pace, but all we need to know is that it is increasing. And then again, they've stopped here at least for 4 hours right there. Stopped. Why did they stop? Does this mean that they are at their cousin's house? It could. It could just mean they've been driving for a long time, so they just want to take a nap. I don't know. Doesn't say. But that's what we get to. That's as much as we need for this problem. Increasing or decreasing. Now you'll have to keep in mind that this one we're comparing distance with time. On the assignment, you will have to compare speed with time. And that means you have to consider a whole different interpretation, because when speed becomes flat, you need to know what that means. So you'll expect to see those types on the assignment, okay? So on this one, the graph below shows, well, I guess it's above on this one. The graph above shows the amount of gas remaining in a vehicle over time. On the graph, label any increasing or decreasing. So let's start with that. Let's start with our increasing or decreasing. Increasing, decreasing in purple. And again, increasing would be up from left to right. Decreasing is downwards from left to right. And so right here, this line, this part of the line right here, that's decreasing. Now, right here, I guess you could say this is increasing, but it happens in an instant, right? I don't know anyone that can fill up the gas tank that fast, but I guess one of these are compared with hours. That's possible. So you're welcome to put increasing right there, but it's just a moment in time, so I'm not actually going to mark that. But I will show right here that somehow the gas remained the same. Now, why would that happen? Maybe they've stopped somewhere to get something to eat. Maybe they've stopped at a friend's, who knows? But they filled up and then met their friends, I guess, somewhere and took a nap, maybe even something like this. But the amount of gas in the tank, in the vehicle, didn't change right here. But then, see, it's going to decrease again. Not only did it decrease here, but it decreased at the same rate. So however they're using the gas, they're using it at the same rate as this one. How do we know that? Because the slopes are the same, right? But that part right there is decreasing. All right, well, tell the story of the graph, no problem. Okay, so just like I was saying, just by doing a quick analysis right there, we see that the gas in the beginning, I'll say how much it even started with. That's where we're looking at this point right here. That's our initial value, the y-intercept. That's right between 20 and 16. That's 18 right there. So we got to start with 18 gallons. And used up all the gas. And it looks like it took that 8 hours right there at the bottom in the x-axis. At 8 hours. In 8 hours, right? Because that's when they have 0 gallons. So they're going to use up all the 18 gallons in 8 hours. Then they're going to fill up the tank and not use any gas. And I'm looking at the blue line right there. That's from 8 to 12. That's 4 hours. For 4 hours. Okay. Then they're going to start moving again. That's when they start using the gas. Then they use, I don't know who they use, but someone. Then they use the gas at the same rate before. And again, that's because we're looking at the same slope. on both purple lines. Using up all the gas in the next 8 hours. So they are empty tank at 20 hours. Boom. Now that's not a very fun story. It's not a very exciting story. It doesn't have like not introducing any characters. There's not like there's a climax here and then some kind of funky ending. Doesn't keep you on the edge of your seat. I don't care. It's a math story, and that's about as boring as you'd expect a math story right there. Boom. Okay. Now, do you have to be that specific? I would recommend that you are, because the sooner you can learn how to read graphs like this and then determine the story, then the better off you're going to be, because you need to be able to make your own assumptions. Okay. Like I said, if you let people think for you, and when you look at graphs, they say, hey, look at this graph. And look at all the gas they use, and maybe they say it's a bad thing. Look at how much gas they used and how fast they used it, and we should go burn down their house. I don't know, something like that. Don't do that, by the way. But they'd say something really mean about those people, or they'd say, look how they could switch the story. Look how nice they use their gas at such a constant rate. It's so pretty, and then it makes you feel good inside. It's like, oh yeah, it's really good. It's really good. We should take those people some flowers. Okay. But you need to make your own assumptions about these. Just look at the graph and then make your own assumptions. And then actually figure out what the story is, because if people start giving you graphs, you need to figure out what the crap that is. I can sketch and interpret graphs from any situation. And again, this is so that we won't be tricked when people use graphs against us, which is usually the case.